Now we were discussing about basically brushing through the concepts that you already know on negative feedback from E250, and where we ended in the previous lecture, this is where what we were discussing. So if we have a feedback loop, where now G and H are frequency dependent, right? So G of S, let's say H of S. So in our case, I'll simplify it. In our case, H is not H of S. In our case, H is mostly the resistive divider that we were talking about. So in this case, it becomes slightly simpler. It becomes slightly simpler because loop gain is mostly dependent on now G of S times H, not G of S times H of S. But that's a mere amount of detail. I mean, you can also have a case where you have H of S. However, from your understanding of control systems in E250, you already know that evaluating this feedback loop, particularly if this loop gain or the open loop transfer function has multiple poles, is not trivial, especially if it goes to second order, third order, fourth order, fifth order, and so on, right? And sometimes it's not even possible to locate the roots of the polynomial if you have if you are going to orders above 3. So in those cases, what do? We then say that we'll resort to semi-graphical methods. And when we say that we resort to semi-graphical methods, we essentially say that we'll evaluate the loop gain, that is the open loop transfer function. How do you evaluate loop gain? So you have to first ground the input. It's not necessary to have an input because loop gain is a property of the loop. Input is irrelevant. You can apply in this block diagram, you can break the loop anywhere because there is no loading effect in a block diagram. And apply a V-test, find out the voltage that is coming out, which is V return, and evaluate loop gain as V return over V test, negative of that. So once you have this, you will have L of S in some graphical form, or you can have it in a polynomial form and then plot the graphs. So typically, if it's a in low pass nature L of S, mod of L will look something like this. And this is there is an inherent assumption here. Inherent assumption is it's a first order roll off. We have only one pole. Now, when you have one pole in L of S, then you will have one pole in the closed loop transfer function also. Now, single pole systems are easy to evaluate. I mean, you don't have to break the loop and find out loop gain to figure out how the closed loop transfer function is going to behave like, because poles in a single pole system or system of order one, finding them out is quite trivial. So even if it's trivial, there is a lot of information that we can extract from the loop gain plot and project it to the closed loop gain case, right? So the closed loop gain case is this. So you have Vi, you have G of S, H. Yes.
Why are we doing that V-test and V-return for just evaluating the loop gain?
Yeah, so okay, what other ways of evaluating loop gain experimentally do you know?
Okay. You were taught like directly multiplying that GS and that function HS
Yes.
to evaluate the.
Yeah. So this is assuming you know explicitly what G of S is and H of S is.
Okay, here we don't know that.
It's quite possible that you might not be able to evaluate them separately.
Why are we not applying that V-test on that positive?
You can apply it anywhere, doesn't matter. It's not necessary that you have to apply it here.
Like why you just break that thing, H and this, and you applied that V-test over there?
No, I mean, in this block diagram, you can as well break it here and apply. You can break it here and apply it. You will get the same GH, right? Ultimately, if you go around the loop, what are you going to get? So you are going to get here minus V test. You are going to get this is G times V test, negative of that. And this will be minus GH times V test. right? And since you are going down the loop, it doesn't really matter where you break. You can break anywhere. Now,
You just have to find that G and H.
yes, so the ratio of V return over V test negative is GH, right? So the entire, all this thing we are doing to find out GH, because ultimately we are replacing, I mean, we have already done it once, we have replaced the G with a differential amplifier, right? So when you have a differential amplifier and H is also loading the differential amplifier, H is a resistive divider, for example, then you exactly don't know which is G, which is H. But as it turns out, product of GH is comparatively easier to find, right? You break the loop, apply, and then figure out what returns. The ratio negative of that is L of S, right? So, I mean, I understand what you are trying to say. If you already know G and H, why bother, right? But the issue is in practical systems, it's almost impossible to know what is explicitly G, what is explicitly H in circuits, not necessarily for example, if you have a couple of mechanical systems connected where there is, in some cases, might not have loading effect, then it's okay, right? But I mean, even in mechanical system, let's say you're building a bridge and you don't take loading effect into account and it loads, it can break, right? So you have to take that also into account. Loading effect is there everywhere, but in different context. Okay. So, so the whole purpose of going by this loop gain thing from here to there is because if you have a higher order L of S, then it becomes difficult to find out the roots of V naught over Vi in a closed loop system. So in the closed loop system, this can be written as this. And I'm sure you know that if L of S, let's say I say that L of S has poles at P1, P2, P3, all real poles. Let's say I found out, I give you that L of S has real poles at P1, P2, P3. Where are the poles of 1 plus L of S? Do you think it is easy to find, or it is, I mean, mathematically slightly difficult job? Let's say you know let me give you an even trivial example. Let's say L of S is S plus 1 times S plus 2 times S plus 3, let's say. Right? So the poles of L of S, or roots of L of S, are at -1, -2, -3. Can you intuitively, without taking much time, tell me what will be the roots of a 1 plus L of S is? It's not trivial, right? So the problem is the roots of this, the roots of this need not even be real, right? And you have to, and it will probably become even tougher if I do this, right? Roots of L of S, -1, -2, -3, I don't even have to do any calculation, but roots of 1 plus L of S is probably, you cannot even evaluate analytically. And as it turns out, the thing that we are looking for is roots of 1 plus L of S, because ultimately we will look for a closed loop response, right? So since it is mathematically difficult to find out the roots of 1 plus L of S, we try to evaluate the properties of L of S and then extrapolate our knowledge of L of S to 1 plus L of S. If let's say tomorrow some mathematician comes up with the theory that I can easily evaluate 1 plus L of S, then the entire control system, the way it is being taught, will change, right? So this 100 years or more than 100 years of control system theory has its foundation in the way it has been taught, is because roots of 1 plus L of S are difficult to find. Okay? Okay. So let's continue. So now we are trying to find out. We are trying to find L of S, plot it, and trying to find out what will be the equivalent expression, not only the expression, what will be the equivalent system behavior for V naught over Vi. Now, V naught over Vi is this in time domain, in frequency domain, or in Laplace domain. Ultimately, we are interested in what's going to happen in time domain. Okay. So all these multiple steps, multiple hops are necessary in order to figure out intuitively, without doing too many calculation, what will be the effective time domain output of a closed loop system when, let's say, I put in a impulse step input. Okay. Okay, fine. So now the thing that we already know is, let's say, in this case, I apply a step input, and let's say it is a first order system. I know that V0 is going to start and end somewhere, and this height will be 1 over h approximately. This will be 1 over h when the loop gain is infinity. If the loop gain is not infinity, there will be an error. There will be a steady state error between whatever is expected and whatever you are actually getting. That steady state error is a function of the DC loop gain, right? I think you already know this. So this steady state error is a function of the DC loop gain. If I have to reduce the steady state error, I have to increase the DC gain or the low frequency gain. So let me draw this clearly here. This is time, and this is step response, right? This is V0 of t, not f. So this output will go something like this. And let's say this is supposed to be 1 over h, but you will have an error. The steady state error will be a function of DC loop gain. Higher the DC loop gain, smaller the error. Infinite DC loop gain means zero error. Now, the other thing that we need to be that we are looking for is we want this settling from here to the final output to be as fast as possible, not as slow as possible, right? So what determines that? We saw in the previous lecture that this is determined by the omega UGP, or the gain crossover frequency, right? Higher the omega UGB, faster the settling. Lower, because ultimately the UGB, omega UGB or omega U of closed loop transfer function is equal to minus 3 dB frequency of closed loop V0 over Vi. Sorry. Omega UGB of open loop L of S, let me write. Omega UGB of L of S translates to minus 3 dB frequency of V0 over Vi. So if I plot V0 over Vi here, this used to happen in the first classes. So when, if I plot V0 over Vi over here, I should get something like this. So minus 3 dB frequency of V0 over Vi is effectively equal to the, not effectively, is exactly equal to the 3 dB omega UGB of the closed loops, open loop system for a first order system. Okay. So which essentially means that, I mean, if you have a first order system and you know that its pole is located at some omega UGB, you can then directly correlate it with a first order low pass RC filter. And in a first order low pass RC filter, the pole translates to time constant, inverse of the time constant, right? So essentially, the time constant of the closed loop system, so this tau is 1 over omega U. Again, note that this tau is that of a closed loop system, omega U is that of an open loop system. Okay, so you see, from the thing that is easy to evaluate, which is the open loop transfer function, we can extract information how the closed loop time domain behavior will be by simply looking at certain parameters. That is why the loop gain is extremely important. The other thing that is also extremely important is if you put a system in negative feedback, a high gain loop in a negative feedback, it can become unstable. And a first order system never becomes unstable, but a higher order system can become. And the reason of instability is, so let's say I draw multiple poles. So let's say I have one pole here, one pole here. This is mod of L, and this is the angle of L. So it's quite possible that so it starts off from 0, hits one pole, goes to minus 45, hits another pole, goes by another 45, and this is 90, another 90. And by the time you reach UGB, you approximately hit minus 5. right? So essentially this becomes minus pi. When this becomes minus pi, what you essentially see is L by 1 plus L at S equal to j omega u is equal to infinity. Minus 1. L of S is minus 1, means this becomes infinity. When this becomes infinity, essentially you say that even though you don't have any input, you can have certain output. Gain of infinity means with zero input, you can get certain outputs, right? So which essentially means that your system is unstable. And we saw in the previous class that it's going to oscillate at a frequency of omega u. Okay. So now the entire game is to ensure that when you're trying to make an amplifier, we don't want it to oscillate. So we have to stay away from this condition. We have to stay away from this condition of when I'm hitting the unity gain frequency, I have to look at the phase and see how far away from minus pi we are, right? And that difference, how far away from minus pi we are, is called phase margin. Next, that's the margin you have, right? Before your system reaches instability, right? You can think of it like you have gone on a trek in a cliff, right? And you don't want to walk at the edge of the cliff. You want to be slightly away because slight amount of gush of wind can make you fall, right? It's equivalent to that. You don't want to be at the edge of instability. You want to be further away from it. The another reason why you want this is because it's not only about absolute stability. It's about how nicely your system, final output settles. For example, when you do a second order transfer function, so let's do that. So let's say your G times H is A naught over 1 plus S by P1 times 1 plus S by P2. Okay. So what will be your V naught over Vi? V naught over Vi is 1 over H times 1 by 1 plus 1 by L. Now, writing in this form helps because ultimately, otherwise the poles come, the terms of S doesn't come in the form of 1 over S, right? So it's sometimes helpful to write closed loop expression in this form. So if I do the math, this will come out to be 1 plus 1 over A naught so if I club them together, I should get S squared by A naught P1 P2 plus S by A naught right? So again, at S equal to 0, that is omega equal to 0, we get DC gain. So we get DC gain. So what is the DC gain in this case? DC gain of the closed loop system. So V naught 0 by Vi 0, which is a DC gain, a low frequency gain. This is 1 by 1 plus 1 over N, right? So if A naught is high, sufficiently high, this is 1 minus 1 by N naught. So you have a steady state error of the factor of, not a factor in this case, your ideally it should have been 1 over H times 1, but it's 1 over H times 1 minus N, right? So this is the cause of the error. So that error can be minimized by increasing A naught. Now, if A naught is sufficiently high, and we are not interested in finding out steady state error, then in this expression, I can neglect 1 over A naught. But if you are interested in finding out steady state error, then I cannot neglect 1 over A naught, right? So you cannot neglect anything with respect to 0 if we are trying to figure it out, right? So that's the, that's how we have been approaching this course. So if I ask you to find out, give a circuit and ask you to find out what will be the steady state error, you cannot assume A naught to be infinity. But if I ask you that find out V naught over Vi over S, and I ask you for some other parameter other than steady state error, then you can assume A naught to be infinity, because you see that in this in this equation, if a naught is much higher than 1, there is not much harm if I neglect 1 over a naught with respect to 1, unless s equal to 0. Okay. So that's what we'll do. So let's say V naught by Vi. This is the closed loop again. So this is something that you have to keep track of, which is closed loop, which is open loop. This becomes 1 over H times 1 by S squared by A naught P1, P2. Now this expression, you should be able to recognize very easily, right? So if I write it, especially in this form, so this is of this form that you are familiar with. Right? So zeta, what is this? What is the significance of this zeta? Damping ratio, right? So if zeta is, for example, 0, so if I hit it with a step, V naught and time. So if I hit the system with a step and zeta is, let's say 0, then what you'll expect is something like this guy will go and start oscillating. And need not necessarily be oscillating around 0. It can do weird stuff. It can do this and keep oscillating, right? So this is zeta equal to 0. Now, if I keep on increasing zeta from 0, so this oscillation will eventually die out. So it will probably be something like this. And I'll not sketch this, guys, because they are anyhow useless. So we're not planning to design a system for a case where the amplifier keeps on oscillating. So zeta equal to 0 or zeta close to 0 is something we are not bothered about. So when does the system kind of starts settling cleanly? What is that called? Critically damped case, right? So for critically damped case, zeta is equal to 1. This is critically damped, right? And slightly below critically damped, what happens? This will go and you'll have a slight overshoot, undershoot, and eventually it will settle, right? And if I keep on increasing zeta above critically damped, it will become overdamped, right? So this is underdamped, this is overdamped, and the center pi is critically damped. Now, in many applications, I shouldn't say most, in many applications, you want the final settling to be as fast as possible without overshoot, right? So in that case, critically damped is the case that we are looking for. Okay. So for critically damped case, if zeta is equal to 1, how does it translate to P1 and P2? Note that P1, P2, A naught, these are open loop properties, right? These are properties of LFS. Okay. So then if I then basically equate these two guys and find out, so your omega n becomes under root A naught P1, P2, and 2 zeta omega n becomes P1 plus P2. So your zeta becomes 1 over under root A naught under root P1 by P2 plus under root P2 by P2. Okay. So now, if you want to make zeta, right? Yeah, right. Thank you. Yes. So now is it possible to get zeta equal to 1 if A naught is very high? Because ultimately we want A naught to be very high. We want we want steady state error to be close to 0, right? So assume A naught tends to infinity. right? Or A0 is much greater than 1 instead of tends to infinity. If A0 is much greater than 1, what should happen to P1 and P2? That is the open loop P1 and P2 to ensure that your zeta is close to 1, the zeta equal to 1, let's say. No, I'm asking, what will be the, can you comment on the relative locations of P1, P2? So if P1 is almost at the same location as P2 and A0 is much greater than 1, what can you comment about zeta? Closer to 0, right? Severely underdamped system, right? So if A0 has to be much greater than 1, then the natural outcome for a designer is, conclusion for a designer is P1 cannot be around the same location as P2, right? So that should be evident from your existing knowledge of phase margins also, because if A0 is very high and P1 and P2 are close by, and if you plot the phase, you should see around UGB, you will hit minus pi, right? So these two observations correlate, right? So if A0 has to be much greater than 1 and zeta has to be approximately equal to 1, then P1 cannot be close to P2, right? So what is the only natural solution? Say, have the P1 and P2 to be far apart. So we need to have one dominant pole, right? You should have one P1, either P1 or P2 to be much smaller than the other, so that I need not have both of these terms. If I have both of these terms, then I have a problem. I have to eliminate one of the terms and then find out the condition for zeta equal to 1, right? So then if let's say assume P2 is much greater than P1. I mean, you can assume the other way around, there is no difference. If P2 is much greater than 1, then I can say zeta is equal to 1 by 2 under root A0 underscore P2 over P1. And here, if zeta has to be equal to 1, then P2 becomes 4 times A0 times P1. Right? So what is the design implication? The design implication for L of S is, if I say P1 is here, P2 has to be somewhere way outside, where P2 over P1 is 4 times the DC gain. If the DC gain is supposed to be 100, P2 should be 400x away from P1. If the DC gain is supposed to be 1000, P2 should be 4000x away from P1 to get a zeta of 1 or a critically damped case. So now the other comment, I mean, now the natural thing to ask is, since everything is dependent on where the location of UGB is with regards to how fast the system will settle, whether the system will be actually be stable or not, then we need to also figure out where is the omega u or the omega UGB or the gain crossover frequency of a second order transfer function, right? So if I have to find out the gain crossover frequency, now I understand that this is of this format, A0 by 1 plus S by P1, 1 plus S by P2. How do I know? How do I know whether omega u is between P1 or P2 or away from P2? What I'm essentially saying is, how do I know whether when I'm simply plotting this transfer function, I don't actually know where the omega u is, right? Unless I evaluate for each frequency point. So when I'm doing pen and paper approximate mathematics, how do I know whether omega u falls here or omega u falls, maybe the plot is supposed to be something like this. Omega u will fall here. How do I know that? So the way to know that, go about doing it is, again, use Bode approximation. We assume, let's say the omega u falls in between P1 and P2. If omega u falls in between P1 and P2, what will be, so by the way, what will, even before we assume that, what is the expression of, approximate expression of this part of the line segment? This is the case where I am bothered about frequency points, which is higher than P1 and lower than P2. So how can I approximate the loop gain formula or the expression? And say this is A naught by 1 plus S by P1 times 1 plus 0, right? Because we are talking about frequency points lower than P2. So if this is the case, then I can basically knock this guy off. And for this part of the segment, this approximates to 1 by, or rather, I mean, I can even knock this guy off, right? So this is also not required. And for the lower part of the segment, after we hit P2, this will become S by P1 times S by P2. Now, if omega u falls between P1 and P2, I should have a solution of this equal to 1. So if this solution exists, then S is equal to A naught times P1. So now I figure out whether S equal to P1 is the right solution or not. If it is not, then I move my attention to the next part of the line segment and then see if this is equal to 1, then your S will be, or I should say in this case, mod of S, because this is all mod. S is a complex number. This should be under root A naught P1, P2. Okay. So now in our case of critically damped condition, where do you think omega u is? Note that P2 is 4 times A naught times P1 for critically damped case. Do you understand the question? That should be clear, right? Whether you understand the question or not. Okay, the question is this. So I'll not draw the x-axis. Let's say I am plotting L, right? So I know the locations of the poles of L are at P1. This is a priori known to us. It is at P1 and it is at P2. So I know this will go like something like this. I need to evaluate at what point of this curve do I hit 1, right? So you have certain magnitude here, certain magnitude here, certain magnitude here. So I am interested to find out where is the gain crossover frequency, right? In a computer, it's easy to do. You punch in the value, you plot, you see, right? But if I have to do on a pen and paper, what is the easiest way to figure out where in this plot is the gain crossover frequency? Okay, so if, and assuming that A naught is much greater than 1. So this is A naught. So naturally, I mean, you don't have gain crossover frequency in this segment. So 2 other segments remain. So is the gain crossover frequency in this segment or in this segment? Yeah. So to evaluate that, I find out the equation of that segment, which is A naught by S by P1, and then equate it to P2, where in our case, we know what P2 is. Sorry, it's equated to 1, not P2. We're trying to evaluate the UGB. We equate to 1. So your A naught becomes, or S becomes A naught times P1, or in this case, mod of S, because that is anyway an approximation. So given that it's a critically damped system, in a critically damped system from our those closed loop equations, we know that P2 is 4 times A naught P1. Where will your UGB location be? In between that, in the middle segment, right? So it will be here. So essentially, your UGB will be somewhere here. And this is equal to 4, this is equal to A naught times P1. Okay. So the other way of looking at the relative stability is, so for critically damped case, that is for zeta equal to 1, this is for closed loop. L of S, this is for open loop. L of S P2 is 4 times omega u. Right? So again, why I'm writing in this format? I'm writing it in this format because what will be the phase margin of this system? The phase margin of the system, what is the general expression? You find out what is the angle at gain crossover frequency, subtract is from minus pi, right? So what is the angle at the gain crossover frequency? You will have minus tan inverse omega u by P1 minus tan inverse omega u by P2, right? So if you have A naught to be much greater than 1, then can you comment on this term approximately? Again, if A naught is much greater than 1, P1 is here, omega u is here. So ratio of omega u over P1, tan inverse of that. This is much greater than 1, close to 1, much less than 1. Out of the 3. Much greater than 1, right? So tan inverse, a large quantity is, come on. You cannot be forgetting trigonometry so early. Minus pi by 2, approximately minus tan inverse omega u over P2. Now, if you want to make a very good system which has negligible steady state error, right? You would expect A naught to be much higher than 1, which means you expect omega u to be much away from P1, which means that you generally don't have to bother about the first term because tan inverse of that term will almost always be equal to minus pi by 2, approximately. What you have to bother about is that excess phase term, this one, because omega u and P2 need not be far apart from each other. And this guy, whichever is giving you the excess phase, can cause an issue if, let's say, omega u is much higher than P2, right? If P2 is way inside omega u, right? If P2 is at much lower frequency, then this guy will also give you minus pi by 2 phase. So you essentially get a total phase of minus pi if omega u is far away or P2 or the second pole is way inside your unity gain frequency, right? So that is another intuition as to why you don't want second order response around the UGB of the loop. If you have a second order response of the UGB of the loop, which means this term is not negligible. Okay, so when I say second order response, what I essentially mean is this. Mod of L, let's say I look at the mod of L and I find that my computer gives me this plot. Right? What can I comment? Immediately I can look at it and say that minus tan inverse omega u by P2 is not negligible. In fact, this omega u over P2 is more than 1, which means this is more than minus 45 degree, that excess phase, right? So in this case, I know that my angle is greater than angle at UGB is greater than minus pi by 2 minus pi by 4. Okay, so if this is the case, which means what? Not only can you now comment whether this is critically damped, under damped, over damped? So for critically damped, where do you want the P2 to be with regards to omega u? Right, so that is the first check, first sanity check, right? Omega u P2 cannot be, a second pole cannot be before UGB. If second pole is before UGB, system will not settle properly. Okay, in an all pole system, a second pole cannot be before UGB. If the system, if second pole becomes before UGB, you have a problem. So if this is the case, then then we need to, that is why these concepts of phase margin come into picture, right? So now what is the phase margin for this particular case, for our case? So phase margin is minus pi, or rather phase at omega u minus of minus pi, right? So essentially this becomes pi by 2 minus tan inverse omega u by p2. So the whole game of stability in negative feedback system is to ensure that the second pole, or if you have additional poles, the phase lag due to the additional poles become as small as possible. Okay. Any questions? Give me a moment. Okay, so by the way, do you have a class after this immediately? Okay, so we'll have a SRS. So Shubham is on its way. He will conduct it. So I don't want to put the circuits right now. We'll do it in tomorrow's class. Any questions based on any of this? So let me come back to the first question that he asked, that why do you have to bother about G and H if you already know them? The reason we don't know them is because if we go back to our negative feedback system and we have this guy is here, then it is not very intuitive to figure out which is G, which is H. And let's say I have another capacitance here and I have another capacitance here, then it becomes difficult to find out what is G, what is H. But it is not so difficult to find out what is GH, because what I'll do, I'll find a place to break the loop. So let's say this capacitance is here. I'll find a place to break the loop here. Apply a V test. Find out V return, not V naught. And then evaluate, basically find out KCL, KVL, and go around the loop and find out V return over V test. Negative of that, it is L of S. And once I have L of S, I'm in the control system domain. Right? We put all the knowledge or existing knowledge of how to figure out phase margin, how to figure out steady state error from L of S. And if we are not satisfied, we go back and look at the system from the perspective of how can I change the L of S. Right? I go back and change. If I, let's say, for example, I figure out that A naught is not high enough for our steady state error purposes, I have to go and increase the gain. Now, one way to increase the gain, for example, you already know, is I can increase the length of the transistor. If I increase the length of the transistor, the gain, intrinsic gain of the transistor increases. If the gain of the transistor increases, that's a good thing. But the issue is, if I only increase L, I will have a lower GM. If I have to restore GM, I have to increase W also. Now, if I increase W and L by the same amount, I increase capacitance. If I increase capacitance, then you see the omega U L of S will start getting affected. If L of S start getting affected, you have all these bad things that you had talked about, right? So that's essentially the trade-off of analog circuits, right? So you figure out what you want, you figure out what you don't want, try to go towards things that you want and not go towards things that you don't want. Okay, I'll stop here. Thank you.